Welcome back, everyone. Thank you for being here today with this next talk in our school. Today we have the pleasure to be with Dr. Chuang. He is an experimentalist in astronomy. He obtained a PhD in laboratory astrophysics from Leiden University in 2018. After that, he was a postdoctoral researcher at the Max Planck Institute for Astronomy, and then he became an assistant professor working in the Laboratory for Astrophysics at Leiden Observatory. His research aims to understand the physico-chemical evolution of interstellar carbonaceous dust and ice under non-energetic and energetic processing, facilitating the extraterrestrial origin of important prebiotic molecules on early planets like our Earth. Koju, how are you?
I'm good. Yeah, thanks.
Thank you very much for accepting this invitation. We are extremely honored to have you here today with us, giving us this talk. I will put your presentation up. If you can go to your presentation on presentation mode.
Okay. Just click the button. Okay.
Okay.
I suppose now everyone can see the full screen.
Yes, thank you very much. We are hearing and seeing very well.
Okay, cool. That's good. So many thanks for the introduction. It's my pleasure to have this opportunity to talk about my laboratory's research, particularly on the interstellar ice and the recent progress in the lab. I'm an experimentalist, as introduced, and currently work in the laboratories for astrophysics at Leiden University. On this Wednesday, we have heard another speaker by Gustavo talking about the UV photolysis of interstellar ice. It was a nice talk, so I think I can skip some very introduction. But if you heard something similar, forgive me. Yeah, that means it's very important. So the key questions in astronomy is how we originate. In astrophysics, we may ask how galaxy, star, or planet is formed. In astrochemistry, we wonder what is the chemical process happen leading to the molecular species in the space. The motivation pushing us forward is the big question on the origin of life. In today's talks, I will focus on the story taking place in the solid state in the very early stage of the star formations. There are so many different research approaches to address this big question about the origin of life. It is a Friday, so let's pick up the interstellar ice. That is the one I feel the most interesting and entertaining one. To do the laboratory research, first, we need to simulate the similar condition, but in space, you can find the various physical parameters. The two most common parameters we mimic are the gas density and the temperatures. So you see the gas density came from the 10 to 5 to 10 to 22 cubic centimeters, or the temperature range is also very wide from 10 Kelvin to 6,000 Kelvins. Of course, if you want, there are more details expected to consider, such as the cosmic rate or the magnetic field, etc. So chemical is important to know in laboratories for astrophysics what we can do and what we cannot do yet. Yeah? So first, spectroscopy. This is the basic tools in astronomy. Most of the observation relies on the interaction between the light and the material. So here, if you are the physical chemist, that will be a plus. The second thing we can do in the laboratories is chemical reactions. We detect some interstellar species, including molecules as simple as hydrogen or complicated as amino acid. And it needs someone to tell us how, where, and when it formed. Yeah? This is input highly relies on the chemistry and the biology knowledge. The final one is the physical or chemical parameters, such as ionization rate, destruction rate, formation rate, or reaction rate. Those values are obtained in laboratory studies in physics and chemistry. So Astronomy is a highly interdisciplinary field. The collaboration with experts in different fields is always beneficial, but it's important that everyone need to speak in the same language. I'm not talking about the spoken language. I'm talking about the language is based on the scientific truth that can be repeated and reproduced in experimental measurements. So let's start with a brief introduction about the star formations. The evolution of the star formation is shown in this illustrative diagram. For people not familiar with this topic, I will guide you through the journey of the star evolutions. So let's start with the top left one. It's called the interstellar cloud. In these pre-stellar stages, most species have converted into a molecular form and supposedly accrete on the dorsal grain because of the low temperatures. And later, interstellar cloud will collapse to form the protostars due to the gravity. And later, the concentration of the material will release the solid-state molecules back into the gas phase. That's how a lot of the interstellar molecules have been detected in these protostars regions. Due to the conservation of angular momentum, the rotating material, such as interstellar dust or interstellar molecules, will lead to the formation of protoplanet disk, and eventually result in the solar system containing the comets, planets, and meteorites. Okay, so in these talks, I will address a few key questions in astrochemistry. Why we study the interstellar organics, and where, or I should rephrase it, when do these organics form? And hopefully, in the end, the research can provide a better understanding of their origin. So far, there are more than 240 molecules successfully identified in the space. The list of the detected molecules are shown in these tables. So let's have a detailed look. It's covered from the simplest diatom molecules, H2, to complicated carbonaceous material like fluorine or PHs. Yeah. The fluorine are the C60, C70s, and the PH is polycyclic aromatic hydrocarbons. So why astrochemists or astrobiologists are most interested in a certain organic species? That is, these interstellar molecule species are considered as a starting point to form the building blocks of life. For example, molecules with amines groups, NH2 groups, and aldehyde groups, HCO groups, and alkyl groups, OH groups, has been successfully detected in the interstellar medians. And these observations are generally contain more than 6 atoms. They are referred as complex organic molecules, of course, in astronomical perspective. So we are talking about the species like methylamine, with amine groups, glycolaldehyde with HCO functional groups, and ethylene glycol with OH functional groups here. And these species are the molecular backbone of building block of life. That is amino acid, monosaccharide, that is the sugar, and maybe the backbone of the lipid. Later, under the ideal environment condition, for example, our early Earth, these life breed can assemble to form micromolecules, including the protein, ribonucleic acid, RNA, and the cell membranes through the biological reactions. So, as an astrochemist, I will ask how and when do these interstellar organics form? But for the astrobiologists, they might be interested in the building block of life, and for the scientists in origin of life, they are more concerned about the micromolecules formation in the early planet. So, in today's talk, I will only focus on the interstellar complex organics. Since we are studying the interstellar origin of the organic molecules, what do the observations tell us? So observation by the ALMA telescope toward the low-mass protostars, and the space exploration mission, like the Rosetta mission to the Comet 67P, and they might give a hint on the interstellar molecules' origins. So in these diagrams, it shows that the detected molecules concentration in the comets are shown in the horizontal axis, and the molecules detected in the protostar are reported in the vertical axis. Yeah, such a one-to-one correlation between the chemical compound observed in the protostar and the comet suggests that these species, including water or aqueous or aldehyde or even the nitrogen-bearing species, all have the early origins back to the interstellar molecular cloud. So this conclusion matches well with the observation showing the existence of the interstellar ice in molecular cloud. It is revealed by the ice vibrational transition as shown in this IR absorption spectrums. So you can see beside the water vibrational mode, which can be well deconvoluted for the CH stretching, CH bend, the OH stretching, OH bending, or the vibrational mode. There are other several IR features can be identified as carbon monoxide, carbon dioxide, and methanol and methane. So in this December, JWST, a new powerful telescope will be launched in terms of the sensitivity and the resolution. One of the goals is to unprecedentedly reveal the composition of interstellar ice, particularly by identifying the fingerprint of the CN-bearing, CO-bearing, and CS-bearing complex organics. So the question is how these molecules will form in such a diluted and extremely cold environment. That is a key question in the astrochemistry. So we talked about the possible formation route, so either in the gas phase or in the solid phase. Molecules, of course, can be formed through the gas phase reaction, like the ion molecules reaction, forming the CO plus and later convert to HCO plus. If the electron will neutralize the HCO plus, we form in the neutral carbon monoxide. However, due to the typical low gas density in the space, such reaction mechanism is limited by their concentration, or we can say limited by the collision possibilities. Another limitation is the excess energies after exothermic reactions. It might result in the further fragmentations. Another chemical scenario is called the solid state chemistry. And the reaction that takes place on the interstellar dorsal grain through the atom molecules reactions. Unlike the gas phase route, this dorsal grain acts as a third body to dissipate the excess energies and to provide a catalytic effect on the surface reactions. Some very common molecules are formed through this route, such as the most abundant molecules like hydrogen, water, methanol. In general, the gas phase routes are more likely to form the hydrogen-pooled species, and in the solid state reaction lead to the hydrogen-richer product. So here you can see the two famous examples is water formation and the methanol formation. In translucent clouds, the non-energetic oxygen atom will accrete on the surface, and they react with hydrogen, forming the OH radical, and then saturated water formations. Yeah. When the temperature drops due to the density increases, the newly formed carbon monoxide, the carbon monoxide is formed in the gas phase, and it will accrete on the dorsal grain because it's the 10 Kelvin, and will also react with hydrogen, forming the formamide and the methanol. So you might wonder, how is it possible the molecules can react with atoms with activation barriers? So the activation barrier we see here, the CO hydrogenation, is most likely through the hydrogen tunneling effect or the catalytic effect of the carbonaceous dust. So here I show the animations about the water formation in the space. This is a simulation based on the WISH project. In interstellar cloud, the dorsal grain with a typical size 0.1 micrometers at extremely low temperatures, atoms can accrete on it with enough lifetime and diffuse on its surface. You'll see the hydrogen accrete on it will react with oxygen atoms forming OH radical and react with another hydrogen forming the water. So in the end, the water will, the entire dorsal grain will be covered by the water surface. So when we talk about the astronomy, public people normally will think about the astronomical observation. And if you ask the people in academia, they will say, okay, beside the observation, there could be a modeling, yeah, as a very important research approaches. In these talks, we are talking about another pillar. It's called the laboratories of research. And it's less people realize astronomy is also a discipline that strongly relies on the experimental data. It is a so-called astronomical triangle, including the observation, modeling, and the laboratories. So I will go through an introduction about the laboratories astronomy, particularly showing the implication in the field of astrochemistry. Laboratory study can provide a solid evidence to support the astronomical observations. For example, you can see the IR the spectroscopy identification of the interstellar molecules in the range from the UV to the submillimeters. In the left top corners figures, the rotation spectrum of the CH2CN is used to identify the observational transition toward the TMC1, the very famous typical molecular cloud. Molecular study can also provide highly accurate physical-chemical parameters. The right figures show the photodissociation rate of the CO molecules as a function of impact UV photon energies down to the order of the -3. This is a very important mechanism to maintain the gas abundance in an extremely cold interstellar cloud, where most of the gas species should contain in the solid state. The laboratory's astronomy simulated the chemical reaction taking place in the space and provide the reaction rate constant. In the bottom figures show the interactions between the carbon monoxide and H atom at several astronomical relevant temperature from 20 Kelvin to the 70 Kelvin. Is explain the formaldehyde and the methanol formations. In addition, experimental studies obtained the chemical parameters like the molecular binding energies on the different material surface, and these values are crucial for astronomical model to simulate the comprehensive interstellar evolutions. Laboratory studies contribute to the astronomy by providing the fundamental information about the chemical roadmap, the spectral details, and the close cooperation with observation and modeling works. In the later slide, I will show the few selected experimental apparatus used in the laboratories for astrophysics at Leiden and demonstrate how they attack the astronomical questions. So the first setup is called Erosis. It is used to support the observation of interstellar ice detected in the star-forming regions. The name Erosis stands for the infrared absorption setup for ice spectroscopies. Here is the pictures of the setup. The principle of this setup is explained by this schematic drawing. Erosis is a UHV setup with the base pressures down to 1 - 10 milliwatt. That's relative to the space condition, about 10 to 7 per cubic centimeters. At the center, you can see there's a substrate and is fully controlled between the 15 to 300 Kelvin. It is used to mimic the surface of interstellar dust grains. The chemical samples are deposited onto the pre-cooled substrate through the vapor exposure at 50 Kelvin. The ice samples will be formed on the germanium surface with a typical thickness around 100 moles. The deposit ice sample is monitored in situ by the Fourier transform infrared spectroscopy (FTIR). The IR solution spectrum shown in these figures is recorded at the center at certain temperatures. As you can see here, acetylene, CH3NH2 IR spectrum are shown in the right figure at 2 different temperatures, at 15 Kelvin and 100 Kelvin for the amorphous and the crystalline methylamine, respectively. The spectrum's position and the peak width of each absorption features are probed as a function of the temperatures. Besides the IR spectroscopy, Erosis is also equipped with a helium neon laser to measure the refractive index or the ice thickness in the laser interference measurement. By looking at the interference patterns, we can calculate the thickness and also with the refractive index. And the measurement spectrum of the pure sampled or mixtures with other astronomical relevant ice provide a spectroscopic database for identifying the molecules in the interstellar ice. As I mentioned before, the JWST will be launched in December, hopefully, and the spectral range from 2.5 to 20 micrometer is ideal for the future JWST observation, especially using the near spect and the MIRI instruments. Marina is a PhD student working on Erosis. Let's hear what she said. Please play the videos.
Hi everyone, I'm Marina Hashid. I'm currently a PhD candidate in the Laboratory for Astrophysics at the Leiden Observatory, and I will talk about my PhD research project on the spectroscopy of complex organic molecules in interstellar ices. So my background is in chemistry and physics. I did my bachelor in Brazil, and I did a master in astrophysics and physics with some projects in astrochemistry. And now I'm doing my PhD in experimental astrochemistry in Leiden. So about the topic of my research, if you see pictures of the interstellar medium on the internet, you're usually going to find pictures of molecular clouds. And nowadays we know that molecular clouds are gigantic clouds of gas and dust material. And inside this clouds, the temperature can be as low as 10 Kelvin. And so atoms and molecules from the gas, they can stick on this dust material of the cloud. This dust material is made of silicates and carbonaceous material. And so you're going to form a layer of ice. And these ices are composed mainly from water, CO2, methane, carbon monoxide, but you can also have that more complex species are formed there. And that's very interesting because you wanted to know the composition of these ices, since molecular clouds are the birthplace of stars, and this dust material can eventually will eventually end up in comets, and it can end up in planets and other bigger bodies in the new form planetary system. So the way we see these ices is through the infrared signature of these molecules. So if you have a young star that emits a lot of infrared light, this light can pass through the molecular cloud, and part of the light will be absorbed by this ice material. So here you have an example of a spectrum of a star, and you see some bands here. These bands are absorption of the molecules that are in these ices, and you see that they are attributed to carbon monoxide, to water, for example, to methanol. So there are a plenty of molecules that were detected and identified in these ices, and every molecule has its own infrared signature. So if you know this fingerprint of the molecule, we can look at the observations, we can look at the spectrum of stars, see these absorption bands, and we can identify what's in there. So my PhD, that's where my PhD comes into play. So in the lab, we can recreate these ices inside the vacuum chambers where the temperatures are very like where we have very cold temperatures around 15K or even below, and the pressure are also very low. So here you have a schematic picture of one setup that's especially designed for study this spectroscopy of ices. So you have a vacuum chamber, and in the middle of the chamber you have a crystal where the ice is grown. So this crystal is infrared transparent, so light goes through, and on the other side you can detect the light that was absorbed by the material that was in this ice layer. So basically we can put whatever molecule we have in there. So we try to reproduce astrophysical ices with molecules that we would like to identify, and we see the infrared signature of this molecule, and then we compare with observations. And this kind of work is very important because if you wanted to look for future astronomical data with more powerful telescopes, as James Webb Space Telescope, that's hopefully will bring us amazing data, we should have the spectra of these molecules taken here on Earth to compare with data that James Webb will bring us. Yeah, that's it.
Okay, so let's thank Marina to give such a comprehensive and very detailed introductions. So can you please switch back to the slides? So the next setup is surface side. So surface reaction simulation device. From its name, is specialized on the surface reaction taking place on the interstellar dark surface, especially the atomic reactions. Surface side is ultra high vacuum setup as well, with a base pressure of down to -10 millivolt. At the center, a gold-plated substrate is fully controlled between the 8 to 450 Kelvin to simulate the surface of the dark surface. The detection tools are the IR spectroscopies and the mass spectrometers. So we're talking about atomic reactions. So how we generate atomic atoms, such as hydrogen. The hydrogen atoms are generated by the thermal cracking source. So as you see that we inlet the hydrogen molecules will output the hydrogen atoms. On the other side, we also have the oxygen atoms can be produced through the plasma dissociations. Yeah, so we inlet both the atomic species into the reaction chambers. And then because it's a low temperature, both species can stick on the surface, and then the oxygen atom react with the hydrogen forming OH radical, and later associate with the hydrogen to forming waters. The chemical roadmap shown here from the simple oxygen atoms can be converted to the OH radical and eventually fully saturated water formations. But also in the space, we have like O2 species, or we also have the ozones in the interstellar medians. And those species can also react with hydrogen, forming different kind of oxygen bearing species like HO2, H2O2. But eventually, all these oxygen bearing species will end up with stable waters. So that's why the water is the most abundant species in the interstellar ice. So the same H-atom addition reaction has been applied to study the ammonia formation. Yeah, so if you look at ammonia, it contains 3 hydrogen atoms. Yeah? So the nitrogen atoms can associate with hydrogen, forming the NH, NH2, and eventually saturated with NH3 product. Similar reactions can apply to the C atoms reactions, successive hydrogenation, convert a single C atoms to the methane CH4. The hydrogenation not only limit to the atom-atoms reactions, but also apply to atom molecules interactions. The reaction barriers is overcome through the quantum tunneling, as I explained before. CO hydrogenation to form the HCO with activation barrier around the 1500s. And later, HCO will react with H atom forming H2O. This is a barrier reaction. H2O can also interact with hydrogen with activation energy about 2000, and then forming the CH3O, and later recombined with H atom forming the methanols. The same atom molecular reaction has been applied to the NO. Yeah, it's a nitrogen oxide. It also can react with hydrogen and end up with NH2OH. It's a saturated product, but also can react with oxygen, forming different kind of nitrogen oxide. On the surface of the interstellar dark surface, the reactions doesn't take place individually. The reaction could have interactions with each other. All the investigated reaction could with chemical networks from the simple atoms to the saturated molecules like the water, ammonia, methane, methanol, all these saturated products. So here I want to go a little bit of details on the CO hydrogenations. CO can be converted to the formaldehyde H2CO and the methanol CH3OH as shown in these IR absorption features. The interaction between the H atoms with these three molecules CO, formaldehyde, and methanol also leads to the abstraction reactions. So it means the formaldehyde can be hydrogen abstracted to form HCO, methanol can be hydrogen abstracted from the CH2OH. Such a forward and backwards processing between the CO, formaldehyde, and the methanol significantly increase the lifetime of these intermediate radicals such as HCO, CH3O, and CH2OH. So if the radical concentration high enough in the solid state, they can associate each other without the diffusion. So basically, the radical recombinations forming the glycolaldehydes and also can explain the methyl formation and also the ethylene glycols. And both complex molecules has been successfully identified by the IR spectroscopies even at 10 kelvins. This formation mechanism doesn't require external energy from the start or the cosmic ray. It has been expanded to study the real sugar formation because the real sugar must contain 3 carbons, that is glyceroldehyde and sugar alcohol glycerol formation. So for the biological relevant ribose, that also could be the automated product from this hydrogenation of the CO molecules. So let's hear Julia to introduce herself, who currently works on the setup. Please play the video from the Julia.
Hi, I'm Julia. I'm a PhD student at the Laboratory for Astrophysics Group in Leiden University. I'm Brazilian. I was born and raised in Rio de Janeiro, Brazil, where I did my bachelor's in chemistry. Then I moved to São Paulo to do my master's in astronomy, and now I'm here in the Netherlands doing my PhD in experimental astrochemistry. So in my PhD, we basically try to simulate the chemistry that happens at the surface of interstellar ices, and we try to study those processes. And through that, we hope to understand better the chemical evolution of the interstellar medium. So let's take a quick look through the experimental setup that I use in my PhD now.
Okay, so please switch back to my slides. So we have a lot of Brazilians in our groups in these years. So the last setup presenting today is called Matrices. It stands for the Mass Analyzing Tool for Reaction in Interstellar Ices. As indicated in its name, the experimental setups use mass spectrometry to study the relevant chemical reaction in space. In previous setups, they all use IR spectroscopy to identify and monitor the ongoing ice chemistry. For example, the water molecules has a strong permanent dipole moment, therefore it's very ideal to probe the water by IR spectroscopy. However, for molecules without the dipole moment, such as oxygen, or the same for the nitrogen or the disulfide species, they are transparent, unfortunately, in IR spectroscopy. So how can we identify their chemistry if they really exist in interstellar ice? Now, the mass spectrometry stepped in. instead of looking for the vibration transition of the molecules, we can count molecules by layers of molecular mass. For example, water has one oxygen atom with two hydrogen atoms. The molecular mass of the water is 18. So for the oxygens, it has two oxygen atoms. So the total mass will be 32 mu. This is a technique called mass spectrometry we use in the matrices. The working principle is a little bit complicated, but I try to explain as simple as possible. We need to look at the more details of this schematic. The drawing is very similar to the previous setup, Erosis and surface side. Matrices is a UHV setup with a base pressure down to -10 milliwatt. At the center, there's a substrate can be controlled between the 50 to 300 Kelvin. The detection tool is a time of flight mass spectrometers. That means it detects molecules based on their flying time in the time of flight tube. Across the loops at the reaction chambers in these 3D models, the chemical samples are deposited onto the pre-cooled substrate around 50 Kelvin, forming around 100 layers of water ice. The solid state chemistry is triggered by the impacting UV photon with energy around 10 eV. The processed ice is further ablated by the Yak lasers at 355 nanometers, resulting in a dissorption plume, as you can see here in the gas phase. The dissorption plume is immediately ionized by electrons impact at 70 eV, forming the ionic species. So once it's ionic, we can fully control it by using extraction plate. The chitons are extracted into the time-of-flight tubes on the left side. The ionic species are recorded as by the MCP detectors as a function of the flying time in these time-of-flight tubes, and further convert into molecular mass. So the typical mass spectrum looks like this from the 1 mu to 60 mu. The mass spectrum shows the UV photolysis of the water ice. The parent species is water, and its mass signal can be seen at 18 mu. Different colors stand for the different UV irradiation times, from the 0 up to 10 to 16 photon per square centimeters. So we can monitor the water depletion and the new peaks of formation, such as the O2 and the H2O2 formations. So the O2, we can identify at the 32 mu peaks, and for the H2O2, we can identify the 34 mu. Both are the water photolysis product. But how are we sure they are the photolysis product instead of the contaminations from the chambers? Later, we can use isotope level species. For example, we can use H218O because we count the mass, right? So since we use 18O, we're supposed to see the corresponding mass shift for the daughter species like 18O2 and H218-2. So we can see the parent species shift to 20 mu, and the O2 and H2O2 form at 36 and 38 mu respectively. So we plot the kinetic evolution of the newly formed O2, for example, as a function of UV fluorescence, and compare to the detected O2 concentrations related to the water species. Apparently, the high concentration of the O2, around 3% to 4% in the comet, is still a puzzle. It cannot be just simply explained by the water photolysis. So the third the PhD student Pranjot from India, sorry, has no videos this time. By today's talk, I hope I can convince you that astronomy is a very interdisciplinary field. Astronomy laboratory is a tool to solve the astronomical relevant questions, although I have to admit, there are still a lot of the puzzle waiting us to solve, but this is good because it keeps us busy. The take-home message today has only one point. It has only one point. That is, if you are interested in the laboratory's astrophysics, you always can find one nearby you and start contacting them. Even if it's just a visit or the internship, I believe that will give you very interesting experience and provide you the different perspective to study astronomy. I'd like to thank you for your attention and happy to answer any questions from you as well.
Koju, thank you very, very much. This was an extremely interesting and very well told presentation. Thank you very much. So I have here one question in the chat. It's related with the. It's a question that I have myself. It's related with the reactions that you show. One thing is that, yeah, you can show us that the reaction goes one after the other, and then you have nitrogen, and then you have one hydrogen, and then another, and then another, and then you can create NH3. But how can we ensure that this is the reaction that will happen? How can we tell that at the end, this is not something like N plus H and then a C or an oxygen or something else? How can we be sure that this will go in the way you show us?
Okay. Yeah, so it's very important in the laboratories. We need to have very systematic studies. So we need to select which species we start with and which is the control, what is a reactant we provide. Yeah. So if I heard from your question, of course, in the stellar medians, all these reactions are intervene each other. Yeah, we cannot limit it only in the nitrogen and hydrogen in the solid state. We have other carbon, we have the oxygen. But in the laboratories, we need to select. We need to limit it to the binary reactions. And based on these binary studies, we started to study more complicated species. Maybe we introduced the 3 atom species like the carbon, hydrogen, nitrogen, and we also expanded to the oxygen bearings. Yeah, so it's very complicated. Actually, we also have a study to show the glycine formation. Glycine is the simplest amino acid. It contains the hydrogen, nitrogen, oxygen, and nitrogen, carbon, CNOH. Yeah. So all these relevant elements. So if we can apply these 3 atoms at the same time, we can go up to very complex glycine formations. I hope that answers your questions properly. Yeah.
Yes, it does. Thank you very much. We have here some other questions that started to arrive. So, what should it be the part of an undergraduate student of astronomy that liked the astrochemistry for continuing with his mastery, and is necessary, and what is necessary that he knew? Is it necessary that he knew some chemistry?
Okay. Yeah. So. Like I said, astronomy, especially in astrochemistry, is a very interdisciplinary field. Yeah? So we not only need people have the chemistry background, we also have a physics. We also need to have a biologist background. So no matter what knowledge you have, yeah, because it's a highly technical research approach. So I think it's open to people with different backgrounds and join the team. Yeah? So as you can see, we have a lot of people from the chemistry, biology, and the physics, or even from the astronomy as well. Yeah? So it's an open team. We welcome everyone to join us.
So yeah, the field is quite open, so many things can come into play to help to understand what you are trying to understand. Okay, next question. Under which conditions the gas phase and solid state formation of water have similar formation rates?
Which condition the gas phase and the solid formation of water have similar formation rates? Okay, so if I understand this question correctly, okay, it's like I said, it's either in the gas phase or in the solid state, right? So it depends on the physical condition. Yeah. So if the concentration, if the gas density is high enough, of course the gas phase route is more dominant. But in the such low temperatures, most of the species is supposed to accrete on the surface. And like I said, that the solid state has the advantage because all these reactions must be isothermic reactions. That means the excess energy might further fragment this newly formed product, break into the fragment again. So, for example, if you have a OH plus H forming the water in the gas phase, but the excess energy maybe will break up the water into the small fragment again. So in the solid state, that's a different story because we have the Darcy grain, and this micrometer size Darcy grain can very efficient to take away the excess energy and preserve the water species on the surface. Yeah.
Yeah, thank you. We have one more question. Is how are lab results extrapolated differently to dark clouds versus protoplanetary disks?
Yeah, this is very very interesting question. Yeah, so all the studies I present today is only limited to the dark cloud. Yeah, so in the dark cloud we have more atomic reactions, but in the protoplanetary disk because the central stars already synthesized and will emit a lot of heat and UV or even X-ray. So in the protoplanetary disk, I think it's the more energetic process that will trigger different kind of solid state chemistry. But as I mentioned before, it really depends on which region, which physical conditions you are interested in. Yeah. So I want to quote a sentence from Sander Tillens, and he's a very famous astronomer, and always say, what we study in the laboratories are all relevant. Your challenge is find where is relevant in the space. Yeah. So I hope this is a good a summary of this talk. Yeah, and also very inspiring everyone to study the astronomy.
Yeah, it is a very interesting question as well. I was thinking about it because not everything will work the same everywhere. So you have to take care where do you want to apply the knowledge and how it will work in that particular site. I mean, is it a protoplanetary disk? Is it a dark cloud? And yes, it's very interesting question. In fact, Koju, thank you very much. This was an extremely interesting talk. I think if the students will have more questions, it would be great if they can write you an email and ask you directly the questions. So thank you very much for accepting this invitation. And yeah, let's see you next time.
Okay, thank you. Bye bye.
The logarithm of this probability.